So let's look at how to calculate the entropy change of some process with an ideal gas. As long as we can plot that process out on the PV diagram, that means that we have a process that's reversible. We'll set this up so that we'll be able to use this equation to calculate the entropy change for any process, whether it's isothermal or not. So again, we're going to start with our basic definition that says this infinitesimal change in the entropy of your system is equal to some infinitesimal energy exchange as heat over the temperature at which that occurs. And then now what I need to do is I need to think about, well, how can I play around with Q? So for starters, I can think about the first law of thermodynamics. So the first law of thermodynamics says that the change in the internal energy of our system is equal to Q minus work by. If I solve my first law of thermodynamics for Q, the energy transferred as heat, I get that Q equals delta E plus work by. So I know that in terms of turning this into a differential statement, that means that dQ is going to be equal to dE plus dW by. Each of these terms basically just becomes infinitesimally small elements, and now I need to figure out what to do with dE and dW. Well, for an ideal gas, we've said that you can calculate the entropy change for an ideal gas along any process by taking the number of moles times the molar specific heat at constant volume times the temperature change of the gas. If you want to think about this as differential change rather than a discrete change, then that delta simply becomes a D, that delta simply becomes a D, and so we've got the dE is equal to N CV dt. So we can plug that in there. Work, well, the work done by our system was defined to be the integral from some initial volume to some final volume of PdV. And to get dW, all we need to do is basically undo the integral on both sides of this equation. My differential element of work done by the ideal gas is equal to the pressure of the ideal gas times some differential change in the volume element. The pressure using the ideal gas law is nRT over V. Number of moles, universal gas constant, temperature divided by volume. That's what the pressure is equal to using the ideal gas law, and then that gets multiplied by my volume element dV. So I can plug this in for this dW term. So when I do that, that tells me that dQ, which I need to go plug in if I'm going to calculate out the change in entropy, is given by this expression. Plug dQ in up here. It basically means that I've got two terms. The first one's going to be NCV dt over T, which I need to integrate that from some initial temperature to final temperature, plus, notice when I divide this second term by T, I've got a T on top and a T on bottom. Those cancel. The need to integrate from some initial volume to some final volume of nR dV over V. The number of moles is going to be constant in problems we work. CV is constant, R is constant. Those all pull out of the integral. And so I'm left with NCV times the integral of dt over T. That's the natural log of the final temperature over the initial temperature, plus nR, and again I've got an integral of dV over V, which is the natural log of VB over VA. So final volume over initial volume. So here's an expression that we can use for any process. Right? We didn't have to build in any assumptions about what type of process that it was to calculate the change in entropy for an ideal gas as it moves from state A to state B. We stated up front that we didn't care whether we had an isothermal process or not, but you'll notice if we do have an isothermal process, then the ratio of these temperatures is 1. The natural log of 1 is 0. So this term disappears for an isothermal process. It's also true that here, if we have an isochoric process at constant volume, the ratio of the volumes is 1, natural log of 1 is 0. This term disappears if you have a constant volume process. We can come back now and think about a new way to define a specific type of adiabatic process. Right? So we've seen adiabatic processes that are reversible, we've seen some that are not reversible. But if we have a reversible adiabatic process, so an adiabatic process that we can plot out in our PV diagram, well, one of the things that means is that Q is 0. No energy was exchanged as heat during that adiabatic process. Well, if Q is 0, that means that you got 0 by adding up a bunch of zeros over and over and over again, so dq must also be 0. So when you plug that in, that tells you that the entropy change over your reversible adiabatic process is 0. So when we're thinking about the types of thermodynamic processes that we've talked about so far, isobaric is constant pressure, isochoric is constant volume, isothermal is constant temperature. Adiabatic, again, all the rest of these constant something, constant something, constant something. Adiabatic we've simply left at no energy transferred as heat. Well, if that's a reversible adiabatic system, then we can refer to it as isentropic. So a reversible adiabatic system is a process that happens at constant entropy. So the last thing we want to do is let's come back to talking about the Carnot cycle. We know the efficiency of any engine is given by the equation. So 1 minus the absolute value of the energy transferred out of your system as heat over the cycle divided by the net value of the energy taken in as heat over the cycle. And we said that for a Carnot engine, it works out that this is equal to 1 minus the cold temperature of your engine over the hot temperature of your engine. So here's our plot for a Carnot cycle. It's going to start at state A. It's going to undergo an isothermal expansion at the hot temperature, then an adiabatic expansion from B to C, then an isothermal compression at the cold temperature, and then an adiabatic compression back to state A. Well, if we want to think about the entropy change along all four of these processes, from A to B, our cycle is taking energy in as heat, and so I can calculate the entropy change from A to B as some positive Qn over the hot temperature of the cycle. From B to C, that's a reversible adiabatic expansion. So its entropy change must be 0. This is an isentropic process. From C to D, well, now energy is being dumped out as heat along our isothermal compression. It happens at constant temperature, so I can calculate out the entropy change by just saying, well, it's negative the absolute value of Q out, because Q out itself is negative, over the cold temperature for the cycle. And then the entropy change from D back to A, that's a reversible adiabatic compression. So again, that's an isentropic process, and so its entropy change is 0. Well, I know the entropy change of my cycle is equal to, add up all four entropy changes. But of course, entropy is also a state variable. So in processing around a complete cycle, I know that the net entropy change has to be 0. So when I put this in, I notice that what I get is an expression that lets me solve, and it says that the ratio of the absolute value of Q out to Qn is equal to the cold temperature over the hot temperature. It's thinking about the entropy change for the Carnot cycle that lets us replace this absolute value of Q out over Qn with this ratio of the two temperatures that your cycle runs at.